This is Lab 3 Magnetic Field of Permanent Dipole Magnets. The purpose of this lab is to measure the distance dependence of the magnetic field due to a bar magnet and compare the experimental values to the theoretical values calculated using the Biot-Savart law. Here, the two important physics concepts are distance dependence and this law. The experimental value of the distance dependence n calculated was negative 3.13 meters, and the value of the magnetic dipole generated was 1.96 angstroms meters squared. These two photos represent the Biot-Savart law, and they will be used later on in calculations in this lab. The important observations of this lab were that when the magnetometer is far from the magnet, it measures a near zero magnet field in the x direction, and as it moves closer to the magnet, the x component of the magnetic field increases. In this experiment, the iPhone app magnetometer was used as the magnetometer to measure the magnetic field due to the permanent dipole magnet. The sensor was calibrated along a true magnetic north, and the distance from the magnet to the magnetometer for the given Bx values was found, as well as the magnitude of the off-axis magnetic field and the perpendicular distance d. The Earth's magnetic field was compensated by subtracting B of Earth from the measured y value in the y direction, which is the perpendicular direction. This is a photo to demonstrate the use of the app, and in the next slide, these values that were found were used in the provided Excel file. So the results in the top right show the magnetic field measured on the axis, and the table at the bottom shows the magnetic field measured at a perpendicular distance, and this data was combined to find the net magnetic field. This graph here shows the relationship between the distance as well as the magnetic field and was transformed into a linear line. Then the equation in the Excel calculated the results on the next slide, where y is equal to negative 3.136x minus 14.749, and the value of n is the slope, and the y-intercept is the value of bx. We use the Biot-Savart law, where r is equal to 1 meter, and use the bx value rearranged to solve for k, where k is equal to negative 3.93 times 10 to the negative 7th, as well as the original equation was rearranged to find b, which was mu naught over 4 pi times 2 mu over r to the power of 3, and we were able to solve for mu by that equation with 1.96 angstroms meters squared. And here on the slide I show the equations that were used to calculate said K, R, N, and those values. Here is the code. So in this slide, I created the magnet at the origin by inserting the magnitude of the magnetic moment, which was 2.61, in order to develop a function of the magnetic field. In this slide, I created the observation locations and created arrows to represent the magnetic fields, and those are shown later in the computational slide. The magnetic fields were 2 on the axis and 4 for perpendicular on the axis. And in this section of the code, I created the magnetic field for the 45-degree angle from axis magnetic field. Here's the model. The cyan arrows are the perpendicular ones, perpendicular magnetic fields. The green are the 45-degree magnetic field, and the purple is the on-axis magnetic field. And when comparing the computational model and calculations, it was found that the d values were similar, but the v values were significantly different. So here on the Excel file, we have that the d perpendicular was 0.17 meters, and it was 0.25 using the computational model in meters. So they were pretty similar, but when you're looking at the bx and by measured values and comparing them to the b perps, the two b perps are very similar, of being a negative 2.45 times 10 to the negative 5th. But for bx here on the Excel file, we have 1.55, and by was 5.04, both times 10 to the negative 5th. So the powers were the same, but the values were different. And these theoretical questions were, what if you hadn't oriented your experiment to represent magnetic north and put the meter stick at an intermediate angle? How would the results have changed? The graph would have looked the same as the data's relative, however the differences between the theoretical and the experimental data would have differed. And what if I were to stick with two magnetic fields together and N and run the experiment again? How would they differ? I would have expected the measurements to double or be close to double in magnitude, but in actuality, the magnetic field doesn't really change when an additional identical magnet is added. Thanks.